Either one. Okay? You can write me if you want special papers or to discuss things uh, with me. Feel free to write me. And you have my mobile phone on your WhatsApp. Okay, so my plan for this afternoon is to start going into atmospheric electricity. Uh, so we'll go on until 2:15, and then we have a break, a tea break. I hope it will be coordinated. And then we will go until 3:30, quarter to 4. Is that okay? I hope you are not too tired. If you're tired, we can stop earlier. No problem. But now we start actually discussing what this course is all about, life and lightning, and atmospheric electricity in general begins not necessarily with lightning. Lightning is just the very extreme kind of show of electrical processes in nature. But we have actually more frequent and less violent processes that occur all the time around us. And maybe we are even oblivious to their existence, but still, even in this room right now, some electrical processes are going on and affecting our health and affecting the atmosphere, and we will discuss those. So I'll start now. Okay. Okay, so this is a schematic description of Earth's electrical environment, and by this I mean what happens on the surface of the Earth all the way up into the upper atmosphere at altitudes of around 150, 200 kilometers. So there's a lot of information here, and we will deal with most of it today, tomorrow, until the end of this course. So we have convective clouds and lightning. As I said, this is the most conspicuous part of electrical activity. But in what we call fair weather, non-stormy regions, we have additional electrical processes occurring continuously in the air. Among them, ionization by either galactic cosmic rays or solar extreme UV, as I will show you later, or near the surface from radioactive elements in the soil or even in the building materials that we have. And those ions attach to aerosol particles and affect cloud processes, climate processes, and even our health and mental well-being, as I will share with you new results from research that was just published a couple of years ago. And some of the clouds, not necessarily even thunderclouds, are electrified by themselves. And so we are embedded in an electrical environment. And actually, if you think of it, we are electrical creatures. Our body works on electricity. You know that as biology student or bioengineering. Our nerves, our brain, our muscles are all relying on electrical processes, transfer of charge by ions. You know that better than I do. Okay, so we are electrical. And of course, being embedded in an electrical environment, this causes an interaction. Sometimes it's good, sometimes it's not so good. And we will discuss the consequences of those interactions. Okay, so what are the main sources of ionization that causes air to be ionized? As we speak, here in this room, I would evaluate the ambient concentrations of ions to be on the order of 500 ions per cubic centimeter. That's the average in a clean urban air, not too polluted. Okay? So we breathe air that is ionized, not significantly, right? But still, some of it is in the form of ions. That means negative ions, where an electron was detached, or attached, or positive ions, where an electron was removed from one of the molecules. So the main ionizing agents in Earth's atmosphere are either photoionization by high energetic photons coming from the sun, either in the form of extreme UV or X-ray, galactic cosmic rays, particles coming from the galaxy, from supernova, from exploding stars, and we are actually surrounded by them all the time. Okay? It's kind of bewildering to think that we are bombarded continuously by particles invisible to us, yet they are coming from every direction, not in the same magnitude every day, all the time, everywhere. Depends on geographical location, altitude, solar activity. I will discuss this shortly, but they are there everywhere. So ionizing agents are around us. Solar energetic particles, not continuous, but depending on the solar cycle, you may get solar eruptions and extreme events coming in with bombarding the Earth with a lot of energy, which causes ionization, and what we call geomagnetic storms that can affect electricity, satellites, the health of astronauts in the space station, if they are there. And of course, radioactivity is very prevalent near the surface on land, not on the oceans, on land. So these are the main ionization agents, and they are most effective at different layers. So if I take this from 0 to, let's say, 100 kilometers altitude, we can differentiate where each agent is most active. So radioactivity is close to the surface until maybe 1 or 2 kilometers, what we call the boundary layer, the lowermost layer of the troposphere. Solar UV mainly in this range between 50 and 120 kilometers, and cosmic radiation is much more energetic. So it can penetrate all the way from way up in space all the way down to the surface. And we measure. We have instruments. By the way, many stations around the world form a global network of cosmic ray monitoring stations, also in India and, of course, in many other countries, to monitor this flux, because this flux affects the atmospheric status of the atmosphere, the electrical status of the atmosphere, and that may have some bearing on the climate. So if you look at the profile, this is altitude, and this is the ionization rate. Ionization rate means how many ions per cubic centimeter per second are formed, okay? So from radioactive elements, the most dominant one is the gas radon. I'll discuss it shortly. So radon, almost a couple of ions per centimeter square, but it goes very quickly to 0 as we go up into 3 or 4 kilometers. So it's mostly important near us, near the ground. This is where most of the ions produced by radon are present. Galactic cosmic rays has this profile, that reaches maximum at around 20, 25 kilometers. I will show you my own measurements with the balloons that we did. Okay? And then the solar particles contribute to ionization higher up, and the rate goes way up, almost 1,000 or 3,000 ions per centimeter cube per second, as we go into the ionosphere, what we call the ionized layer of the upper atmosphere. So between the surface and the ionosphere, it's like we are embedded in what in electrical engineering they call a spherical capacitor. Like the Earth is a conductor and the ionosphere is a conductor, and between them the atmosphere is like a dielectric kind of substance, non-conducting. And we can see this profile repeated in many, many diagrams. It goes all the way up to hundreds of kilometers away. I remind you that the formal boundary between Earth and space is 100, this region. But you can see the blue line shows you that the electrical layers of the Earth reach significant concentrations at around between 100 and 300 kilometers. So this is the base of the ionosphere. It's sometimes divided into layers for practical engineering purposes. You can use the conductivity of the ionosphere to bounce back transmissions. For example, if you know the altitude of the ionospheric layer, you can use it for long-range transmission because you know the reflectivity of the layer. So you bounce a signal, incident angle is equal to the bounce level, and then you can actually create a connection after the horizon to very remote stations. And this technology had been used before the space age to communicate very long distances. Of course, now we have satellites, and Elon Musk puts every week new satellites in orbit. We have continuous connection everywhere. So this is basic stuff. I'm sure you know it. Photoionization by solar radiation. You get very strong energetic photons coming in, and above 60 kilometers, you have this photon takes out an electron, and you have a positive ion and an electron out of, and this can be a nitrogen molecule, an oxygen, which are the most prevalent molecules in the air. And galactic cosmic rays is the more interesting ionization agent because it comes from the cosmos, from everywhere. And it is predominantly due to particles with a large atomic mass coming at the speed of light and impinge on air molecules and just tear away an electron. And so at 15 kilometers, the rate is 40 to 50 ions per centimeter square cube per second. And at the surface, it goes down to 1. So the contribution near the surface by cosmic radiation is small. Still, it exists all the time, everywhere, also above the oceans. As we will see, radioactivity is important, but only above land. So when a cosmic ray comes, it hits a molecule, and what we see is what we call an avalanche, or kind of particles are being thrown out from the original atom. Okay, let's say this is a cosmic ray particle. By the way, the term itself, cosmic ray, is a misnomer. It's not a ray, it's an energetic particle. We just call them rays and it confuses everybody, but it's actually atoms that fly through space, probably emitted when stars explode, and create supernova. So the remnants of the star are thrown away in the galaxy in all directions and create this flux of nuclei that impinge on molecules in the atmosphere and create this cascade of atoms and ions and subatomic particles like pions and muons. I don't want to go into that level of detail, but we can actually measure this in the lab. And outside in stations, especially on mountains, I will show you. This is our cosmic ray station. It's on the highest mountain in Israel, 2.2 kilometers, near the Israel-Lebanon-Syria border. A very peaceful place. No. It's one of the most volatile and dangerous places. We have to get permission from the military to go up on the mountain and take data, because this is covered by snow. So we have a detector for cosmic rays, and we measure continuously. And in some events, we have what we call extensive air shower, that you have an increase in the flux of coming cosmic rays that creates more and more ions in the air, and we actually can measure this. So inside this kind of big cage, we have those neutron monitors that can actually count the number of cosmic rays coming from space and ionizing Earth's atmosphere. And we can measure the concentration and create a profile of how many ions are produced. Well, this is much easier to understand. This is the height, this is the count rate. So how many cosmic rays arrive per minute, okay? Particles from the cosmos. So this is from Russia, and you can see that there are two different graphs which show two different years. 1987 in red, flux is higher. 1991, it's blue, flux is lower. But same profile, reaches maximum around 20 kilometers above the ground. So this is where most of the energy brought from space by those atomic particles that we call galactic cosmic rays is deposited. The name is the Fotze maximum, usually between 20 and 25, depending on the latitude of your station. But you can measure it everywhere. If you put a station in the Himalaya, you will measure the same vertical profile of this is from balloons that were launched in this station in Russia. Same profiles. Why is this different for different years? Because of the solar cycle. You know, the sun, our star, has an 11-year cycle of activity. What does it mean? It means that every 11 years we are either at solar maximum or solar minimum. What does solar activity actually mean? It means when you're close to solar maximum, you have many solar storms and solar eruptions, what we call coronal mass ejections, like the sun throws away a lot of particles, energetic particles, that spread in space from specific regions that we call sunspots. They appear on the sun as black spots, actually probably detected for the first time in the 17th century by Galileo Galilei, who was actually the first one to point a telescope at the sun. He was clever enough not to look at the sun with a telescope, but to project a solar image on a screen, and he noticed that there were black spots on the sun, and then they started writing and picturing those spots, drawing them by hand. There are some handwritten measurements made by Galileo in 1610 that are still in the museum today, and they are used to reconstruct the activity of the sun, and we notice this cyclic, periodic kind of pattern. And we've counted 25 cycles from that period. 25 times 11, you can do the math, goes all the way back to the 17th or beginning of the 18th century. Now we are in the middle of cycle 25. So if you look up on the web, solar cycle 25, you will see that the sun is becoming more and more active. Many more spots on the sun, many more solar eruptions, many solar storms. What happens during a solar storm is that the ionization rate in the atmosphere increases so much. You see aurora, the northern lights, going maybe even to 35 latitude north. So you can see in the middle of Europe, like last week, there was a storm so strong, they saw the aurora in Paris, France. This is latitude 44, I believe. So this is, and we've not reached the maximum yet. So solar cycle 25 is coming maybe in 8 to 10 months. The funny thing is that even though we are so sophisticated and so knowledgeable about solar activity, we are still unable to predict when exactly there will be a solar storm or when will solar maximum occur. So when solar maximum is present, the flux of cosmic rays is at a minimum because the sun's magnetic field pushes away the particles coming from the galaxy. So this is why we have different, why we have different years. So when there's solar maximum, minimum ionization by cosmic rays. Solar minimum, you will have maximum ionization. They are opposite to each other. If the sun is more active, cosmic rays are less active, not able to penetrate the magnetic field. This is some of my results that we published. This was my PhD student, Roy. And what we did was launch from the southern part of Israel. We launched balloons. And you saw the video, although it was incomplete, but they go up until 40 kilometers sometimes. And they measure the ionization rate. They have an ionization counter. And you can see that we can reconstruct the same profile as in the previous graph from Russia that shows you how many ions per cubic centimeter per second are formed, and the maximum is around 20 kilometers. So this map shows you the state of Israel. This is the Mediterranean Sea. This is Egypt, Jordan. This is Saudi Arabia. Just a little geography for you. Yesterday I took an Uber, and the driver started talking to me, which is rare, I should say. And he said, "Where are you from?" I said, "I'm from Israel." And I could clearly see that he didn't know where that country was located. So I had to, he said, "So can you tell me what countries are neighboring?" I said, "Okay, so it's Egypt and Jordan and Lebanon." I try to, locate. It happens everywhere. We're such a small country that you have to know exactly what to look on the map to find us. But anyway, so this is in the southern part of Israel. The other slide that I showed you with the snow is located here, this point, on the triple border. Anyway, as I said, balloons are drifting to neighboring countries, not always retrievable, but the main result is this, that you have this profile, and galactic cosmic rays are most efficient around 20 kilometers. Now, I want you to remember this number because I will show you something that was a big debate until a couple of years ago, and still is maybe, that is related to the importance of galactic cosmic rays to the Earth climate. I will soon explain. So this is like a summary slide that shows all the players that are responsible for energetic particles coming into Earth's atmosphere and causing ionization. So it's the sun, it's a magnetic field, it's solar activity. This is a typical kind of depiction of a solar eruption. Luckily, this was not directed to us. It was directed away from us. There's a famous solar eruption that occurred in 1859. It's called the Carrington event. It was so powerful that people could see it with their eyes, like coming out of the sun. There was an enormous eruption. And back in the day, 1859, the only electrical device on Earth was telegraph lines, Morse code. And the effect of the geomagnetic storm and the ionization was so strong that it burned down telegraph stations all across Europe and the US. And people are very, very worried that if today we had such an event, what they call a Carrington event, K-E-R-R-I-N-G-T-O-N, Carrington, you can look it up later, it will burn down most of our satellites. Okay? And to go back, if you burn down GPS satellites, there goes Uber. No taxis anymore. No, it's funny, but think how dependent we are on space technologies today. Even from, showing you a satellite image of a typhoon in Taiwan to ordering Uber to get to Malabar Hills, like I did yesterday. You're dependent on space technology, and space technology depends on solar activity. Because if we will have, and it's just a matter of time, when we will have such an event, will we be able to switch down the satellites or to protect them in time to avoid technological disasters on Earth? No, airplanes, ships, Uber, everything relies on GPS navigation these days. People will get lost immediately. And of course, broadcast and transmission, everything is totally dependent on technology. And a couple of years ago, I was invited to a UK, US, Israel task force that is called EIS, Electrical Infrastructure Security. And I'm not a security person, I'm not an electrical engineer, but I know something about space weather and the effects of solar eruptions on electricity. And they were worried what would happen if a Carrington-style event occurred today. And are we able to predict it? So we are looking at solar cycle 25. We have satellites located in what we call L1. L1 is the Lagrangian point between the Earth and the Sun, 1 million kilometers away from Earth, between Earth and the Sun. So it constantly looks at the Sun and gives us real-time image of the Sun. So when we see something anomalous occurring on the Sun, we have 8 minutes early warning before the energetic photons arrive, because they travel at the speed of light. So we have 8 minutes, 500 seconds to be exact, because we are 150 million kilometers away from the Sun, and the photons travel at the speed of light, 300,000 kilometers per second. Do the math, 500 seconds. That's the early warning that we will get for energetic photons coming from a solar eruption. And then the plasma, the heavier particles, they are flying at 1600 to 3000 kilometers per second, much slower. So we have a day and a half to protect our power lines, our infrastructure, everything from the arrival of a Carrington-style event in modern planet Earth. And so I went to this EIS session, and forgive me for digressing a little bit, but I want to pose this question to you. And we did this exercise with my students. Suppose there is this event, Carrington-style event, that knocks down our power supply, no electricity, but not like we are used to, maybe a couple of minutes, half an hour, and the electrical company will resume. I'm talking about hours to days with no electricity. Can you imagine your life without electricity? What would go first? What would go immediately, almost? This will go down. No network. Wi-Fi and the cellular networks done. Then your battery goes down, your phone is dead. And the electrical doors in your building, if you have one, you're locked. You cannot. Elevators, water pumps to higher levels in your building, electric cars, banking machines, tellers in the supermarket, everything goes down. And in order to kind of educate politicians how dangerous this reliance with no backup. I mean, if you don't have a backup to produce electricity by other means, then the situation can be grave. And they prepared a short video just to educate decision makers and put it in their mind what would be the consequences of what we call a black swan scenario. You probably heard this term, black swan. Black swan is a very rare event that nonetheless has a non-zero probability. Okay, it's very rare, like you don't see black swans in nature. Swans are white normally, but once in a while there is one. Very rare, out of the ordinary, hardly expected, but still you cannot say that will never happen. No chance that a virus will escape a Chinese laboratory in Wuhan and spread to a global pandemic in 2 months. No chance. Oh yes. So that was kind of a thought experiment. So when we talk about ionization and the effects of high energy events, be it from the sun or there are other doomsday scenarios, I don't want to scare you, but there are scenarios that you can knock down a country and bring it to its knees by taking away its electricity for months. I don't want to give you ideas, but this think tank was contemplating all kinds of, I thought, these guys have seen too many war movies or Netflix spy theories, that can't happen. And yet they said, okay, we know that this regime in that country, somewhere in Asia, is contemplating this kind of scenario. Sneak attack that can drive a country completely out of its electrical capabilities. And so it can be a solar eruption, it can be a terrorist attack, it can be a nuclear attack, but the bottom line is electricity is out. And we find it very hard to imagine because we are so used to being digital and being electrical and being online and connected. but try living without electricity a single day. See how you make it. Okay? It's a good exercise, by the way. Think about maybe, in my country, there are communities that have no electricity. In the desert, Bedouins, nomads, no electricity, and they manage. But that's not the way of life we are used to, right? So it's kind of interesting discussion. Let's talk a little bit about something less scary, radioactivity. I'm not talking about Chernobyl, Fukushima kind of nuclear disaster scenarios. I'm talking about natural radioactivity. Actually, I have a very potent radioactive device here. Did you know that bananas contain a high level of potassium-40, K40, which is the radioactive isotope of potassium, K40. Check it out. Bananas, radioactive. Not really, but above average. But the main agent that we should really worry about is radon gas. Radon is a noble gas, a heavy gas, atomic number 86, and it usually is formed from the degradation of radium and other radioactive elements, and usually the degradation of uranium and plutonium, and very close to the surface. And it goes either alpha decay or beta decay and produces unstable atoms that eventually deteriorate and cascade down. And while this process of radioactive decay occurs, you have ionizing radiation that you can find in nature, and you can find that radon can percolate from the ground. I don't want to go into the details. You can look later in the presentation. But the main thing is that because it's in the ground and in elements that we use to build our buildings, it migrates through the soil and can escape into the atmosphere or get trapped in the basement of your building. And this is a very serious health issue because World Health Organization statistics show that apart from smoking, radon is the second largest cause of lung cancer in the world. Okay? Very dangerous. This is why it's becoming mandatory to do radon surveys in every new building that is built, at least based on WHO standards, in order to verify that there's no high level of radiation and ionization that can cause damage to lungs, especially, by the way, to infants, pregnant mothers, and elderly people. More susceptible to this kind of effect by radon, and it's usually here. It percolates from the soil into the basement, and because it's heavy, it's accumulating near the ground. And you don't see it, you don't smell it, you don't taste it. Nevertheless, it's there, and it's all the time ionizing the air around you. And if you are exposed for a prolonged period to ionizing radiation, it will cause mutations in your DNA, and you know the outcome of this. So, the best option, ventilate, is to ventilate and have a circulation of air coming in and going out, taking anything that is related to radon and to its ionizing capabilities. There's a bunch of documents and guidelines on the web. You can look at the EPA site, Environmental Protection Agency, of the US government. They give a huge list of advice, what to do, and how to protect yourself and your property. And it's different from state to state, from country to country, because it relies on the mineralogy of the soil. Some soils contain minerals that have higher radioactivity, and some are less. So you have to be aware, and if you buy a house or build a house, ask your contractor, what is it made of? Where did you get this material? Where is this cement coming from? So these are the ionizing agents that we are surrounded by, and I don't want to scare you too much, but they are everywhere, all the time. Not dangerous, but you should be aware that ions are around us, and they are short-lived in the sense that they are created and then they are transformed into something else. They can either attach to aerosol particles or attach to water molecules and droplets in clouds, and they don't survive as free ions for a very long time. In minutes, they will attach to a neutral atom or a molecule and create either a negative ion or a positive ion. Okay? So we call this process hydration and clusterization, when a neutral molecule or an atom being called action of energy, hit by a photon or a cosmic ray particle or anything, or a radon emitted photon. So an electron is ejected and we are left with a positive ion. The electron quickly attaches to another neutral molecule and creates a negative ion. So we have a positive ion and a negative ion, and those attach to other neutral molecules or atoms, create what we call a cluster. A molecular cluster, sometimes it can be hydrated and collect water molecules around it. And those ions are mobile. They are not stationary. Because they are charged, they are susceptible to the influence of the electric field in the atmosphere, and the speed is dictated by a constant, which is related to the type of ions we're talking about, and the intensity of the electric field. And they are very slow, but still they're moving, and the mobility of ions, the big ions are slower, and the small ions are faster. And why is it important? Because there was a theory, still is, that atmospheric ions can produce condensation nuclei and affect the formation of clouds. And this is important because we can look at this two ways, as I mentioned in the previous lecture. So clouds are formed naturally on cloud condensation nuclei. As I mentioned, they can be minerals, salt crystals from the ocean, pollen particles, dust, biological agents such as microbes and other species. But now we add ions to the equation, and ions can produce additional particles. So those additional particles may actually enhance the already existing particles and contribute to cloud formation. So they were saying the following: if we know that there are different particles that are formed due to ionization, and this ionization rate changes with solar activity, maybe we can look for a signal in the amount of clouds that are formed that corresponds to this change in ionization. Do you understand the logic? The logic is quite simple, to be honest. Ions create particles, particles encourage cloud formation. If the number of ions depends on solar activity every 11 years, wouldn't we expect a global signal in the amount of clouds every 11 years? It stands to reason, because we know this occurs. This had been replicated in the lab. Sure, we know that ionized particles get clustered, hydrated, and can form small solid particles that may eventually lead to the formation of clouds, cloud droplets. So there was a big debate. Maybe 10 or 15 years ago, the original papers appeared in the literature claiming that climate change is not caused by humans, but is a natural consequence of the solar cycle repetitivity, and we can expect that the solar cycle will modulate Earth's temperature because it will change the amount of clouds in this cycle. So solar maximum means, based on this logic, more or less clouds. What do you think? Solar maximum? Less clouds, because less cosmic rays coming in, right? Because of the solar magnetic field. So at solar maximum, we would expect a lower amount of coming particles that can ionize the air, and by this logic, create condensation nuclei that would lead to cloud formation. And some papers that were published analyzing global cloud data, they took huge amounts of satellite images, computed the amount of clouds on the whole planet, and they said that they found this periodicity, claiming that climate is controlled by the sun, not by humans, not by greenhouse gas emissions. It's all the sun. A specific group from Denmark. And it caused a great debate. Papers appeared and some experiments were done, and then they said, okay, let's test this hypothesis more critically. One of the first measurements to be done was to show that the actual maximum of ionization occurs. Remember the altitude that I showed you? Where is the maximum? 20, around 20, 25 kilometers. But this is in the stratosphere. There are no clouds there. Clouds form much lower in the troposphere. So that was an Achilles heel, a very weak point of the argument that, okay, if we have a maximum of ionization at 20 kilometers, how come these ions are short-lived, minutes? How come they can affect the production of clouds lower in the atmosphere? First argument against the theory. Second argument was, let's do this in the CERN nuclear accelerator in Switzerland. You know, this big accelerator on the border of France and Switzerland, where they do this high energy nuclear collisions. And they have this specific cell that they put in the tunnel, mimicking Earth's atmosphere, and saying, okay, we will accelerate atomic particles to relativistic speeds, mimicking cosmic rays, and let's see if clouds will form. And they did this repeatedly, found no effect. So the theory is now kind of sidelined, not being discussed anymore. The theory was ion-induced nucleation and its effect on clouds and climate. It doesn't mean that it does not happen. It could happen. but marginal effect on our climate. I will repeat myself. It's basically us that are responsible to changing Earth's atmosphere, and by that we change the energy balance. I think I will skip this and talk about this. So this is an image taken 2 weeks ago in Marrakesh, Morocco. You know what happened there? It's written. It was a 6.5 Richter scale earthquake. And this time there was like a camera that was pointing towards the horizon, and we saw this bright flash a couple of minutes before the earthquake. And then physicists started looking, what is it? Is it related to anything we know of that relates to ionization in the atmosphere? Could it be true effect? We started looking at data, and we've seen that in many earthquakes, especially the strong ones, I'm talking about 6 and above, those lights appear. And they appear in different shapes and colors. Sometimes they appear tens of minutes before the earthquake. Sometimes they appear during the earthquake, and sometimes after the earthquake. What's going on? It's kind of something that people reported, but no scientist actually paid attention. And it's coming back at us. Because you'll see tomorrow when I talk about high-level discharges in the atmosphere, I will tell you that pilots have seen this decades before physicists actually discovered it. Pilots knew and reported, nobody believed. And the same with earthquake lights. You can look it up now. It's becoming like viral in the social media that earthquake lights exist, and they are related to ionization. 2 possible explanations that are related to what I've discussed now. 2 explanations. This is a paper that was published in 2021, not so far ago, because this group looked at 2 famous earthquakes in Peru and in Mexico, where people swore that they saw those lights. And there were some video images, but not very good. And you know why scientists are naturally suspicious of reports by, let's say, citizen scientists? Regular people pointing a camera, shooting something. We don't know where, when, what was the camera. We just see a video on Twitter, on YouTube, or Instagram. Somebody posts something. Usually it's about UFOs and aliens and all that kind of stuff. And so we are naturally suspicious. But I'm blaming ourselves in a sense that we should have paid attention to those reports because they were consistent. And looking at history, people saw reports from Roman times, from 200 BC, that people saw those lights, different shapes, different colors, different timing. So this paper was published, went peer review, and the authors suggested 2 processes, one of which is release of radon gas. Radon is trapped in the soil and in the ground deep in the earth crust. Prior to an earthquake, when the fault lines, the plates are starting to move, this sudden movement of the earth releases huge amounts of radon very quickly to the surface. And this increase of ionizing gas,
this is a radioactive gas, very ionizing, causes a rapid increase in ionization that may, under special conditions, lead to the emissions of light. One possible explanation. A second explanation, it's coming back, is what we call a piezoelectric effect. Piezoelectric, used in industry, used in many applications, is when you put a pressure on certain types of crystals, they emit photons, radiation. Sometimes it's in the visible light. You can create crystals that if you change mechanical pressure, they emit light. You use it in many remote sensing devices and other applications. And by the same mechanism, maybe, by the way, both are active prior and during an earthquake. And so the question is, can we predict earthquakes using this knowledge? Now that we are convinced that in some circumstances, powerful earthquakes are preceded by light emission near the epicenter of the earthquake, can we perhaps issue an early warning? It may be even minutes, but minutes are critical. You know why? Minutes in earthquake prediction are critical because in emergency management, people use this sentence: earthquakes don't kill people, buildings kill people. If you have a 5-minute early warning, run out of the building, you may save your life. So if we are able to monitor somehow radon concentration prior to earthquake, and maybe the entire electrical profile of the atmosphere continuously, maybe we can come up with a way to alert the public that there's going to be a strong earthquake in the minutes to come. We're not there yet. However, some new discoveries are showing that this can be a true effect. If you look at what happens to the entire atmosphere, from the surface all the way up to the ionosphere, with a satellite, you can maybe notice those changes in advance. We still don't have a full coverage of the entire planet, but maybe if this is kind of tested again and proven to be a true effect, maybe in the future we will have an early warning for strong earthquakes. It's only good for very, very strong earthquakes. So, ionization is not something that is detached from our life, okay? That's my point. It affects our health, it affects our well-being and our safety, either through the radon affecting our lungs or radon as a precursor for movements in the earth. And we monitor the ion balance of the atmosphere because we know it's very sensitive to the presence of particles. As I mentioned, the ionization rate and the balance between production and destruction of ions highly depends on the concentration of particles and is the aerosol concentration. When we have a lot of aerosols in the air, they attach quickly to the ions and diminish the conductivity of the atmosphere, which we can monitor. Don't be afraid, we don't need to solve these equations. It can be solved. I did this for my master's degree. back then, solving those numerical equations, we can produce the ion aerosol balance and deduce the presence of dust by monitoring the electrical parameters of the air. And coincidentally, some people have this capacity by their own physiology to sense changes in the atmospheric ion aerosol balance by feeling it in their body. And it's called the Sharav syndrome. Sharav is a Hebrew word for prolonged heat waves accompanied by dust. Very prevalent in the Middle East, North Africa, Morocco, Algeria, Egypt, Libya, Israel, Jordan, Saudi Arabia. All those desert countries are affected by this syndrome, which is a traveling weather system accompanied by extreme heat, can reach more than 40 centigrade, 42 sometimes, 44, and accompanied by a lot of dust and a very dry air. So this is what we call the Sharav syndrome, and from a science paper I found this quote: as is apparent with those individuals living in the Near East who succumb to the atmospheric ion imbalance because too much dust, ions are taken out, precedes by 24 to 48 hours the dry wind and high temperature of the Sharav weather complex. So people, by their own body, can sense a disruption to the ion aerosol balance of the air. In normal conditions, we are okay. But if there's too much dust, takes away the ions because they attach to the particles, people feel this. Some are more sensitive than others by their own physiology, maybe 10%. The number is between 10 and 15% of people that report this syndrome. It also could be that they are sensitive to the temperature, not necessarily to the ion balance. Okay? But still, it's in the literature and it's been studied many, many times, and I did a research as well. What I studied was the effect of dust on the electric field, not on people's health. I had instruments here in the desert. This is Sinai Peninsula. This is Saudi Arabia, Jordan, Egypt. Israel is here. And I had a station here in the desert. You see this blue point. That's where my station. And what we see is that the blue line is the electric field that tells us something about ion concentration in the air. When the ion concentration is diminished, the electric field increases. This is a consequence of Ohm's law, that we have to keep continuous current in the air. And we see that these rapid fluctuations, when the dust arrives, electric field jumps. And of course, I didn't have any person there to report on his headache or her headache, but this is a true syndrome. It's a true effect. You measure it with instruments. Will it affect the physiology of people? We can study that. I should confess, I looked in preparing today's talk, I looked at reports, found almost none. Maybe I was looking at the wrong journals. It should be medical journals, but very few reports. Probably because people don't report what they feel or cannot distinguish between temperature, dust, ions. It's very hard to tell. But certainly in the desert, this effect may be a consequence of a disruption to the ion aerosol balance of the air. Okay? And now let me surprise you with this. So this is a new paper. I was actually a reviewer of this paper, and I told you, we are embedded in an ionized medium. The air is slightly ionized. Concentration is a few hundreds of ions per centimeter cube everywhere. And so it may attach to our body, it may attach to our clothes, to our skin. We don't feel it that much. However, insects such as bees, much smaller, and they can be highly charged just by flying through an ionized air. And this group from University of Bristol in the UK found evidence for that. It was a theory. Can large swarms of flying insects, flying quite slowly, right? They're not birds, they're not flying too high, it's close to the ground, slowly, and always dipped in an ionized medium. So what they found was that bees, of course this is kind of an artistic freedom, showing lightning between bees, but it's a true effect. This is from the paper. So this is a locust, you know, on the plate. That's millions and trillions of flying insects. And so this is from, I think, Saudi Arabia. And what they did was use a computer model to see what charge would each and every insect would carry, and what would be the cumulative effect on the electric field and on the conductivity of the air. And this graph summarizes everything. On the top is bees, this is locusts, this is butterflies, this is fair weather, this is thunderstorms, below the thunderstorm, and this is dust storms. And they show that the effect of a swarm of locusts or even of bees on the electric field can be as powerful as below a thundercloud, which is amazing. Of course, it's temporary effect because they fly, right? They're not hovering all the time. If you're unlucky, they will be around you. But this is a very dramatic effect that we didn't think exists. But this guy said it stands to reason. Since the air is ionized and we are located in this ionized medium, that animals, insects will be affected. And so it's a brilliant paper. If you want, I can share it with you. Maybe I will upload it to the WhatsApp group so you can see it. It created a sensation in the media because bees create electric fields that are strong as lightning, and of course, very clever artist on the journal paper, like, okay, the media just jumped on it, and of course, they didn't read everything, but it was good. It was good for a while, and it was running on Twitter like crazy. Bees are electrified. Beware of electrified bees. Whatever. Anyway, so let's continue. And talking about the effects of ions on people, well-being. Let me ask you this. When you are in the vicinity of a waterfall, does it improve your well-being, or what is your sensation? If it's not too private, you're at the beach, near the sea, open sea, the waves, you're sitting on Marine Drive with your boyfriend or your girlfriend, and the sea splashes. Do you feel good, or any change in the mood? Well, there's a bunch of reports that people feel much better in the presence of exploding water drops. Something in the air. Romantic, not romantic, I don't know. But if you are near a waterfall, near the shore, near water, there is a chance that you will feel, and most people report that, you will feel good. But there was no conclusive evidence and no thorough scientific study. So you see, this field of atmospheric electricity and human health is rather new. Not much research. There were many reports. People feel, people think, people see, but no consistent database. Anecdotal reports, nothing too concrete. And of course, what is the physical explanation? We are looking for physics or biophysics, the interaction between the medium and the human body. Okay? So, some explanations, and the most prevalent one is the effect of negative ions. Okay? People exposed to negative ions, which means air molecules that attach an electron and by that become a negative ion, report that they feel better, and the possible explanation is the increased production of serotonin in the brain. It's a hypothesis, not proven yet. It's very hard to do experiments, certainly not in humans. You don't want volunteers to be exposed to negative ions while they are in an MRI and you scan their brains to see what goes on. But still, anecdotal reports, a neurotransmitter associated with mood regulation. So if we are exposed to negative ions, then the probability is that something within our body will respond in a way that will make us feel better. That's evidence-based assumptions, okay? And there's also the effect of water splashing, cleaning the air of pollutants and removing all kinds of compounds that may affect us negatively. So just the splashing of water may cause this double effect, either by negative ions released through the splashing of water, I will show you how this happens, or by the removal of airborne particles and pollutants and taking away the bad stuff. So no wonder that in many, many places and parks, people feel better in the presence of water. It's called the blue and green effect. I will show you. Of course, another explanation is that the sound of flowing water acts like a white noise and diminishes the brain exposure to disturbances, reducing stress and anxiety. There's kind of modes of therapy. I'm not an expert, not sure it's working, but you put earphones and you hear white noise and it makes you feel better. Personally, I prefer to listen to the Beatles. That makes me much better. But some people like the sound of flowing water. When I go to my reflexology treatment, she always put this meditative music with the sound of water. But I don't know if it's the sound of water or the fact that she's touching acupuncture points. I don't know. Anyway, and of course the psychological effects of our connection to nature. This is embedded deep within our psyche, and so it's not maybe one that excludes the other. It may be a couple of effects working together, but sincerely, people report feeling better in the presence of water. What happens to water in waterfalls? We call it the Leonard effect, named on the physicist who described it. The Leonard effect, from the splashing on water, shear forces generate stress and produce small negative ions from the exploding droplets. And so when water explodes, the air becomes enriched with negative ions, and the liquid drop remains positively charged. So this is positively charged, but the air is flooded with negative ions, and most people feel good in the presence of negative ions. So it's called the Leonard effect. This is how it actually occurs. Like the collision with the surface explodes the droplet and releases an ion, or the water evaporates and generates equal amounts of negative and positive charges. So either way, as I will show before I summarize today's class, the World Health Organization recommends that for well-being of people, the presence of blue and green, but mostly blue, areas, lakes, ponds, waterfalls, flowing water is beneficial to most people. Okay, and of course, we will discuss this before I summarize. Okay, so let's break for tea now, okay? Maybe 15 minutes, and then we'll go to the second part and finish early. All right? Sounds like a plan?